Welcome to another episode of Code for Thought. Welcome to Season 6 of Code for Thought. If you did have a summer break, I do hope it was a nice and a relaxing one. I'm going to kick off this new season with an episode on Fortran. And I wanted to do this for a very long time, partially because I learned my software development skills with Fortran 77 to be precise, and also because Fortran has this reputation of being an old and crusty programming language amidst all the other cool stuff that's out there. But nothing could be further from the truth. There is a vibrant and very active community of Fortran developers and users out there, as I hope you will see during this episode. And besides, Fortran is of course used in a number of applications in science and research. For this episode, I had the great pleasure and privilege to talk to some of the engineers who are very active in developing Fortran and shaping it to what it is today. You will meet, for instance, Thomas Clune, who is an engineer at NASA and also works on the Fortran Standard Subcommittee, Wim Vanderbauwhede from the University of Glasgow, who worked on optimizing legacy Fortran code. And you'll meet Ondrej Certik and Milan Curcic. Milan has written a book on modern Fortran, and Ondrej is working at GSI Technologies developing compilers. But before you hear from my guests, let's go back in time and explore the roots of Fortran for a little bit. As you may know, Fortran has a long history. It all started in the 1950s at IBM, where a team led by John Backus developed a new set of instructions to avoid having to program in assembler languages. This new language was to be a little bit closer to what you'd expect, for instance, from mathematical expressions and formula. And this, of course, gave it its name, Formula Translation or Translating System, which then morphed into the name of Fortran. The first version of Fortran was published in 1956, and at the time, Fortran was developed for IBM mainframe computers. Additional features and abstractions were added largely by Grace Mitchell for Fortran 2, which was released in 1958. Grace Mitchell is also credited for publishing a book called The Programmer's Primer for Fortran, which proved to be influential for budding engineers and developers. With Fortran 4, it was possible to work on different machines, and from then on, Fortran language versions were named after the year in which they were published, like Fortran 66 and, of course, Fortran 77. Arguably, Fortran 77 is the legacy version most widely spread and used to this day, and it is, as I mentioned before, the version that I cut my teeth on as a software developer. Fortran made it easier to program than, say, assembler, but the language was not without its quirks. These were in part circumstantial. Here's an example. At the time, punch cards were used as input for mainframe computers. They came in different sizes, but there was one type which was used a lot. It was 80 columns wide, where the first 6 columns were used as control bits. And so, in legacy Fortran versions such as Fortran 77, each programming line has to fit within 80 columns of characters, where the first 6 characters were reserved as control bits, and programming instructions have to be fit in between column 7 and 72. And just as a sideline, Fortran was not the only one influenced by punch cards. The first terminals, which then started to replace punch cards like, say, the VT50 and the VT100 from a company called Digital Equipment, were also 80 characters wide. And still today, many command line terminals come with a default width of 80 columns. So spare a thought or two if you open a command line terminal. When I started university in the 1980s, punch cards were still in use. Working with punch cards is of course very cumbersome, and it quite frankly put me off programming for a while. And I'm not the only one. Tom Clune from NASA had a similar experience when he started working with Fortran 77. So over to Tom. So you're working at NASA with a lot of Fortran code, aren't you? And you have been doing that for quite some time, I guess. Probably starting with Fortran 77, maybe even earlier?
Not earlier. In high school, I was able to take a Fortran class at a local university just to do something interesting for a change. And ironically, it almost completely put me off computing because I actually had to use punch cards. And this is already after the era when TRS-80s and Apple II computers existed, and I had experience with those. So it wasn't the language that was off-putting, it was the step backwards in the technology I had to use to do the programming. Fortunately, once I got to college, I was back to using terminals, and I once again enjoyed it. So yeah, I've been using Fortran since 1984-ish, but not heavily probably until I started graduate work probably, or well, no, even in undergraduate a fair bit, and just more and more over time.
Well, luckily, this didn't stop Tom from programming, and far from it. Tom is now a member of the Fortran Standards Committee, and we will hear from him again a bit later when we talk about his contributions, like, for instance, a unit test framework in Fortran. But in the meantime, let's hear from Milan and Ondrej how they started with Fortran. Their experience is actually quite different. No punch cards there. First we hear from Ondrej and then Milan.
Yes, I think my first experience with Fortran was, I think, working on my advisor's code in F77, and I was first wrapping it into Python because I like Python. But eventually, I then realized using modern Fortran is better.
For me, it was in college. I was in a meteorology program back in Serbia. So that was 2006, third year of college, and a lot of numerical modeling and analysis courses went in. The dominant language that was used at our institute was Fortran and still is. It may be interesting that even though it was 2006, I was taught Fortran 77, and I started from there, and thereon I sort of taught myself later and more modern iterations of Fortran.
It's the same with me. It's F77, and I only learned modern Fortran. I believe I was at Lawrence Livermore.
Okay, and finally, let's go to the University of Glasgow in the UK and hear from Wim and his forays into the language.
So I'm Wim Vanderbauwhede. I'm a professor in computing science at University of Glasgow. So I've been in this job for about 20 years, but originally I studied physics, and then I worked as a chip designer. And so gradually I moved into more computing-ish things. So in that role, I've always been particularly interested in compilers and programming languages, and specifically for heterogeneous hardware. Also, as part of the work, I came in touch with people who do scientific computing. And that's how I got into Fortran, really, because it turns out it's still heavily used. It's not great to go to accelerators. So there was an interesting research challenge there. And then I did a lot of work on that.
As you've just heard, we started with Fortran 77, and for good reason, as there still is a lot of Fortran 77 code out there. So in the next section of this episode, I talked to Wim again and his efforts to optimize legacy Fortran code. But don't worry, we'll move to modern Fortran shortly, so stay tuned. And just to finish off our discussion about Fortran 77 and legacy Fortran code, I talked to Wim about his paper Making Legacy Fortran Code Type-Safe Through Automated Program Transformation. I asked him specifically to explain type safety when dealing with legacy Fortran code.
Type safety means that you will not arrive with a situation where you provide the wrong kind of inputs to a function because the type system didn't stop you from doing that. For example, in C and also in Fortran, it's possible to wipe the type information. In C, you would do that by casting to avoid star. In Fortran, you can abuse the common blocks for that purpose. And there are other ways in Fortran besides that. And all of these lead to essentially the type information getting lost. And therefore, you can take data, redefine it as another type of data incorrectly, and still keep on using it. And then the program would go wrong, and you have no way of doing something about that. That's type safety.
Fortran 77, for which a lot of legacy code exists even today, has no type safety in your view, or?
It's not type safe, meaning that you can abuse the type system to do unsafe operations. And that is what happens a lot in actual code. This is the same for C, actually, and it's worse in C because, well, at least in Fortran 77, I could show that you can get around it. In C, you can't. It's impossible.
Okay.
You can't prove that your program becomes type safe through program transformation in C, but in Fortran, you can. So essentially, what it amounts to is that you look for the unsafe operations and you replace them by safe operations. And you have the guarantees because you do this in an automated way that this is truly safe. So the paper contains proofs to that effect.
The question that I have is when people take this legacy code and say, well, we want to upgrade this to, say, Fortran 90 or something later, are these versions of Fortran then stricter in the sense of their use?
Well, they let you be stricter. Fortran has chosen quite radical for very far-going backward compatibility, which is important because of the legacy code, which tends to be very old sometimes, or if it's not old, it's written in an old style. And therefore, they support all the unsafe features. It's kind of the other way around, though, that from Fortran 95 or 90 onwards, there are additional features that make the code type safe.
For instance?
So mostly is the fact that you can do what you previously did with common blocks by using modules. That's one approach, although that's not the approach that I used. But there is a difference in what is allowed when you type check in Fortran 95 and when you type check in Fortran 77. And the other thing is you can actually alias variables to one another. In Fortran 95, you do that in a different way, which is safe. So the question is whether it's necessary to upgrade the syntax to Fortran 95 to have the type safety. And I think what it is essentially that the way types are checked in Fortran 95 is stricter than in Fortran 77, and the compiler makes the decision based on the features. It seemed to work for most compilers because Fortran specs are very loose. The specs are actually more defined by the compiler implementations than by the actual Fortran specification. Fortran specification would let you get away with more than most compilers do.
Okay, enough of legacy Fortran now, and let's move on to the more modern aspects of the language, which we will cover in the next section. Wim already alluded to Fortran 90 and 95, and in fact Fortran 90 was a major upgrade to the previous version. And the new millennium has seen a number of further upgrades, with a new version coming out in fact this year, the year of recording, Fortran 2023. But let me hand over to Milan and Ondrej now, who will take us through the journey Fortran has made over the last few years. First, here's Milan again.
Fortran 90 was the next major iteration of Fortran, and it introduced several really big changes. One was a relaxation of the syntax. F77 before had this thing called fixed form, which sort of forced you to write source code in a certain way, start from the 7th colon. Everything had to be uppercase, variable names had to be up to 6 characters, and so on. Freeform introduced in Fortran 90 relaxed a lot of that. But beyond that, there were several major language features. Some, for me, most impactful was whole array arithmetic. Very much like in NumPy, you could now work with whole arrays without iterating over each elements to do your math. Modules for better organizing and packaging of the code. Dynamic memory allocation. Before Fortran 90, we had to work with static memory allocation, common blocks. Now you could allocate memory dynamically, and derive types to create compound types out of the built-in intrinsic types, which later led to classes in Fortran 2003.
2003 also added the NumPy bracket notation for arrays, which is a minor syntax change, but it's a big in terms of readability because F77, it was a slash and a parenthesis, and to this day I don't remember which way you're supposed to write it. With the bracket notation, it's suddenly, that now it looks like an array. So that's 2003, I believe. And then 2008, I believe, added classes. I use the term class because most people understand what that means. It's a structure that has methods and inheritance, stuff like that. And then I think another big one is co-arrays. Computational Fortran codes typically run in parallel on a big, small or big cluster. Historically, the most common way to parallelize any code is MPI for high performance computing. But what Fortran did is they introduced co-arrays, which I think were initially developed by Cray. Might have been the 90s, if I'm not mistaken even. They wanted a more natural syntax for writing parallel code so that the users don't have to write these low-level MPI calls and handling, so that users can just write array code and just tell it, well, this array is maybe accessing some array on some image, or copying arrays, or accessing arrays, and just using a natural array syntax. Say you are copying some array from some image, the compiler knows that at some point the data will be needed. And it also knows when the data is ready. For example, if the compiler implements the co-arrays using MPI, it can insert the one-sided MPI send at the moment the data is available and put the receipt where it's needed. So it's actually even more efficient than doing it by hand. Typically, when I at least write MPI code by hand, I don't use these one-sided calls because it's extremely difficult to get it right, really time-consuming. And so I just do the two-sided calls, which are blocking calls. You have to wait until the data gets copied. The co-array syntax, in fact, it can even be faster. So Cray, I think they kind of developed this in their compiler, and eventually the committee standardized it in 2008. It's a feature that's not used very often yet, but I think it's a feature that has a huge potential. If compilers start supporting it more and people start using it more, and it has good support on all platforms, I think it's a very nice way to write parallel code. And then 2018 is, I think, the latest standard. I think it's a minor revision, so I just added some fixes to things like parallel loops and added some more intrinsics, things like that.
We are now looking at another version, I believe in 2023, later on this year. So is there also going to be a minor revision, or is there some big changes coming?
Yeah, it's a pretty minor revision. So I noted here for myself 3 features that stand out. We will have simple procedures, which are a more restricted variant of pure procedures, which will further allow you to write even more optimized pure functions. Another one is enumerations. And the third one are conditional expressions, very much like in C, you can have an assignment statement where you do if this condition, then this, otherwise that. But the main thing about that adds to Fortran is that you can do short circuit operations, which previously you couldn't do without if blocks.
Could you explain what you mean by short circuit?
By short circuit, I mean you can make an assignment statement where if the first condition is true, the compiler will follow that branch and not evaluate the other one. So that you could do with basically if blocks beforehand, but if you had to pass conditions as arguments to functions, they had to be completely evaluated for the program to proceed. And in general, for all the new iterations, one of the standard committee members, John Reed, publishes every time a paper called What's New in Fortran this edition. And he had a paper about a year ago, What's New in Fortran 2020X. We still didn't know it was going to be 2023 or 2024. Now it's not. We know it's going to be 2023. But that's a relatively short summary paper of all the new features that are coming into the standard. And that's always a good paper for people to review about what's next.
I hope you got the impression that a lot has happened in Fortran. And in fact, Milan, who you've just heard, has written a book called Modern Fortran, and you can find the reference in the episode notes. But modernizing the language is one thing. What makes a programming language powerful and widely used is, of course, the tooling and the development environments, which is, in fact, what we will talk about in the next section. Ondrej is working on compilers, and of course, compilers are an essential tool when it comes to Fortran and other languages. But I also asked him about other tools and general tooling in Fortran. So here's Ondrej again.
Yeah, I would say that's the most important thing is the tooling. In fact, I realized when I started the compiler is that Fortran as a language is not too bad. It's not ideal, but it is actually, assuming you had the best tooling and best compilers, Fortran language is very, very good. For the numerical computing, I think it's the best of all the languages even today. The issue with Fortran is the tooling and the compilers. And I think it starts with the compiler. You have to be able to compile your code.
Yeah, otherwise.
But you laugh at it. But actually, a lot of our codes, let's say at Los Alamos, they did not compile with every Fortran compiler. In fact, we had codes that only one compiler could compile them. That's just very sad state. So you have to compile it. Then you have to run it on every platform. And so that includes the high performance platforms, the HPC clusters. So it needs to run on GPUs. That's part of the modern HPC computers. And so it needs to run on NVIDIA GPUs, on AMD GPUs. It needs to run on, obviously, Intel. It needs to run on ARM. Also, oftentimes there are these computers, they don't use Intel, they use Power 9 and all others kind of weird architectures. So the compiler has to be able to run your code there. And that already is a tough task. Then the other part of the tooling is the development. So as a user, as a Fortran developer, when you're developing your code, you need to be able to pull in dependencies. These large applications, they have a lot of dependencies. And historically, because the tooling just wasn't there, people just include the dependencies in the application itself. So it's a huge application, it has everything. That's fine for the application, but if you want to have an ecosystem like Python so that you can just import a package for icon solvers and import a package for special functions, e-solvers and loading things and so on, everything you want as a package, then you need tooling for that. You need some mechanisms to maintain packages and publish packages and depend on packages and compile them. To fix that problem, a couple of years ago, we started a Fortran package manager. Of course, we try to model it by the best in the industry, which we think is Cargo from Rust. And so we borrow pretty much all the good ideas from Rust. And Rust also, the Cargo, they build their ideas upon Haskell and NPM from JavaScript and so on. So it's not in isolation. And so FPM, the Fortran package manager, you create a simple, it's called fpm.toml file where you tell it all the dependencies you want. FPM pulls them. You specify typically a GitHub link, and then it compiles them in the correct order, and then it compiles your project. FPM figures out if you use other build systems like CMake or Make or Mason, you typically have to specify each Fortran file, and typically the build system can figure out the dependencies, but you have to tell it so many details. The way Cargo works, and FPM as well, is that you just put your files in a layout. If you put your file in the SRC directory, FPM knows it's going to get compiled as part of your library or application. If you put your file in the app directory, it's going to be the main program. So it's going to be an executable. If you put it in a tests directory, well, it's probably going to be a test. And so FPM knows this, and then it does that, I think, by default. And then if you don't like the default, you can override it in FPM toml or using command line arguments. So it's very, very easy to use it as from the user perspective. We still have to improve it a lot, but it's already usable. I recommend you to test it out and use it. So that's package management. And then the last part is the ecosystem. So tied to the package management as well, but we need people and the community to actually be building these packages. I think it's happening. We have initial packages for the basic tasks. Listeners, if you find something that's missing, please go ahead and create a package and get in touch with us. You can use, if you search Fortran, the page fortranlang.org should come up. That's our main page. And in there is a link to a forum, Discourse forum. There is a very nice community. We started a couple of years ago. And I think there's about 1,000 users already as of March 2023. So we welcome you to join and get in touch with us. If anything is missing, anything you want to help with, please do that.
If you're interested in finding out more about FPM and the compilers for Fortran, well, there are links in the episode notes. But let's move on to the ecosystem, which is what Ondrej mentioned in the last bit, which is a nice segue into my conversation with Tom Clune. Testing your software is an essential part of engineering, and many programming languages such as Python come with unit test frameworks built in, which is where Tom comes in, because Tom developed a unit test framework for Fortran, specifically for parallel computing environments. First, I asked him how he got started. Here's Tom.
I came to that sort of in a funny path. So I would probably consider myself typical of most scientist programmers up until that time, in that I knew what unit testing was, sort of. I didn't have a lot of experience with it. It sounded like a lot of trouble. At the same time, as I had some fairly embarrassing gaffes in my career by then, where I had significantly optimized somebody's code, but it no longer got the right answers, and I didn't know why. That was something that sort of primed me to be ready once I got the right exposure. And then the sort of seminal event was we got a new contract at NASA for the software developers that were in my group. Brought in a new contractor, and their manager was a bona fide software engineer, and probably the first such person that I had ever worked with closely. And he dragged me to something at the time which was called Software Developer Best Practices, which looks like a conference on paper, but in practice, it's actually well-paid tutorials for a week of experts in all sorts of areas of software engineering. So I got exposure to people like Kent Beck, who was sort of the inventor of the idea of test-driven development, got exposure to actually doing test-driven development, albeit in a language like Java that I only knew enough to be able to read. But I came away saying, I get it now. And then mostly just to prove to my colleague that didn't think you could do things like this in Fortran, I set about and actually wrote a very small framework that looked a lot like how you bootstrap Java's JUnit framework. And then just also coincidentally, just everything sort of gelled at the moment. Somebody came by that wanted us to help him convert his Python code to Fortran and parallelize it. It was a very, very simple scientific model. It was for simulating the growth of a snowflake. It was mostly just using symmetry. So it almost looked like a cellular automaton. The paper was written to write unit tests to describe it. I threw this unit testing framework, and so I sat down and said, okay, each of these pieces, I sort of know what they need to do. We wrote pieces. I wrote tests first, made sure things that worked. And, it was probably only a 2,000 line code altogether, which in the grand scheme of things is nothing. But the amazing thing from my point is that it ran on the very first attempt and essentially got correct answers at that point. The lie that's behind that statement, though, is there was lots of debugging, but the debugging was all of the development of these just individual pieces. And I had never had an experience like that before. I usually wrote 2,000 lines and then spent weeks or months troubleshooting. It's called PF unit. I wanted to call it F unit, but another group at NASA, a different center at NASA, sort of simultaneously put in an open source request for their own unit testing framework in Fortran. Slightly different design methodology and not really focused on HPC, MPI stuff. So there was enough non-overlap that we couldn't really unify our experiences, but they had the namespace. So I put the P in to stand for parallel. And this was still before object-oriented Fortran was reliably existing, right? It was after the 2003 standard had been ratified, but the compilers really didn't have the functionality, certainly not reliable enough to do complicated things. But I kept pushing on it. And once things became reliable, then there was a major rewrite where this time it was not so much test-driven development. This was like, okay, the people that did JUnit knew what they were doing. They've got a good design. I'm not going to try to match their design expertise. I'm going to take what they did, emulate it in Fortran, and put in the necessary extensions to do the things I want, like MPI in particular, which is critical for my work.
In addition to PF unit, Tom also worked on a template library for Fortran. C++ developers will be familiar with the concept of a standard template library. So here's Tom again talking about his work on the Fortran equivalent.
So, and this is one where I sometimes have to fight with the Fortran community's preconceptions. Software containers are wonderful things in certain contexts. And Fortran, of course, actually does have one very, very good first-class container. It's called arrays. In Fortran, you can have an array of any type. It can be multidimensional. There's lots and lots of really, really nice things that Fortran arrays do. But there's times when they're not quite the right solution. And so a common pattern I see in scientific infrastructure is that you don't know how big a set of things you're going to have when you actually hit run. The code that was driving me to do this at the time is something called GIS Model E. It's one of the climate model that was first used, in fact, to warn Congress that climate change is a real thing. There, they have a number of places in the code where people have basically said, okay, I want to add another diagnostic here. I want to add another atmospheric tracer here. And so they had this logic. It worked. K equals K plus 1, blah, 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 blah. And they had a maximum size of the array. And if you ever got too big, then you threw an error and that told the person to go increase the size. And so I was looking at it saying, this is sort of tedious. There's a lot of duplicated logic. And so I started developing sort of a very poor man's preprocessor-based library just to do vectors of this. There was another person that had just arrived there, a guy named Doron Feldman. And he was actually a professional C++ software engineer. So I got the benefit of this extremely experienced C++ person that was also frustrated with the same things for the parts of the code that he was working on. I would sort of, lend him my Fortran expertise and he would lend me his container expertise, and we sort of both pushed each other, and we ended up something which was much more general than what I would have ever attempted to do in the first place. Right. It was still a mess. The preprocessor is not a great way to program these things. It's not a real equivalent of templates. Once the dust settled and I realized I was going to use it for lots of other projects, I then went and did a complete rewrite of that as well, just to make it so that it was at least possible to debug. It is not a friendly code to look underneath, but users don't need to do that. Users can now come along and say, here's a data type that I'd like to use as a value. Here's a data type that I'd like to use a key, and you can define a dictionary or a map, whatever you want to call it. And by and large, it works. My second rewrite also, I tried much harder to be as close to the C++ standard template library interfaces as I could, mostly because I hate writing documentation. And I felt like, well, if I do that, then I can just tell people, well, go read the C++ documentation and then put on your Fortran filters for a few things which don't look Fortranic. And I have found that to be an incredible multiplier in my work. It let me develop several other open source libraries efficiently.
Yeah.
I use it routinely in my current work. I've even had converts within my own group, and I didn't try hard to push it on them.
And I think it's called GFTL, isn't it?
That's right. Once again, I couldn't use the name I wanted. I wanted FTL. I can't remember who already had FTL out there, but there was already an FTL, which, science fiction fans, I just thought that would be a clever little thing. I couldn't put the S because it's not standard. It's just my own template library. So I did G for Goddard. Sort of another aside is, so I lead the subgroup on the Fortran committee that is developing generics features for Fortran. And this project is largely why I ended up in that role. I would like to be able to do containers the right way in Fortran.
In short, a lot has happened in terms of tooling and development environments, but there is still room for you to shine and contribute. So if you like to roll up your sleeves and get busy, there are pages in the episode notes for you to follow up on. And in the next section, I want to focus on where Fortran is actually used in practice. In terms of where Fortran can be deployed, I first talked to Milan, who encourages us to consider Fortran for machine learning and AI applications. So Milan, in an email exchange we had, you mentioned machine learning.
Mm-hmm.
Machine learning, people associate Python with it. How does Fortran come into it in your view?
That's a great question. So I think the need for Fortran comes into machine learning mainly through existing Fortran applications and their need for machine learning. There are many very large software projects that are written entirely in Fortran and that are running operationally for various needs of the public and society. Closest to me and the most common and well-known application of Fortran to the end user, the general public, are the weather forecasts. Weather forecasts are under the hood generated by very large Fortran programs that run on large clusters in parallel. The data comes out of them, and that data is processed into graphics, text summaries, advisories, all kinds of products. The recent, let's say, past 10, 15 years, rapid development in machine learning, new methods have been developed to either accelerate computationally expensive physics modules or the entire solvers, and they can be accelerated by training a machine learning emulator that approximates the solution of the full deterministic physical model, but basically allows you to compute something, let's say, 10 times as fast. If we can deliver a weather forecast, incoming hazardous weather, that means that we can either deliver important information to the public much quicker, or if we can keep the same time to delivery of the advisory, for example, we could use a much richer, denser, high-resolution model to compute within the same time.
And therefore sort of be more accurate in the weather predictions and the weather forecast.
Exactly. So we could be faster or accurate or more accurate or both. So how can we fit in machine learning into that? Most models are being trained in Python. How do we apply them? How do we run inference in Fortran? And there have been many, many different ways people have done it in practice. In general, the most common way to do it has been to just train in Python and then save your model in some file format. Then you need to code explicitly the inference code in your Fortran application. There lies in the need for either intermediate, sort of a bridge Fortran framework, or a dedicated Fortran framework for machine learning that can do training and inference. Because it's not only about the need for inference in Fortran, it's also that there exists a community of machine learning practitioners that would actually prefer to do all their machine learning work in Fortran. But they use Python because of the rich ecosystem and all the tooling. I am not myself a machine learning practitioner, but I have a curiosity for these things and how they work. So during the writing of my book, I thought, I was writing a chapter on derived types, and I thought my editor always coached me, always have a concrete example. So I thought neural nets could be a good concrete case for derived types. Maybe this is an opportunity for me to learn it. So in the book, I followed a tutorial. I implemented neural nets in Fortran. I wrote a chapter. Like what came out of it is that during the writing of that 80-page monster of a chapter, I also wrote this MVP of a small machine learning framework in Fortran that could do only feed-forward, fully connected neural nets, but it could do training and inference And even with my just naive, the simplest implementation without any special tricks to optimize, it was already competitive performance-wise and a few times better memory use-wise compared to TensorFlow.
You're throwing the gauntlet out there.
Yeah, so an editor of a Fortran journal invited me to write a paper about it. That seemed interesting. So I did that. When I wrote a paper, very soon after, I started getting emails from people saying how they found it interesting and useful. It got noticed a little more. There came in another framework specifically to bridge Keras and Fortran for climate applications. So that was a collaboration with a team from UC Irvine. So between that and my original paper, this has been cited over 100 times, I think, and applied in over 20 published studies. It has a track record, and I managed to get a small grant from NASA last year to expand the feature set. Right now, it's sort of on a hobby project level. Some people are contributing to it, but I am looking for further opportunities to fund the work to build it further. I think it does have great potential.
Apart from machine learning applications, Fortran is used in a number of applications that require big computing power, and in particular in earth sciences, climate and weather modeling, areas where both Tom and Wim are active. But can or should Fortran be used for everyday applications? I asked Ondrej that question.
I view Fortran as a domain-specific language. It's still general purpose. You can write any code in Fortran. We wrote the Fortran package manager in Fortran. You can write a web app in Fortran. You can do anything you want in Fortran. But the strength of Fortran is for array-oriented numerical computing. So anywhere you have array, numerical computing that's not symbolic but array-oriented, it will be amazing. If this is not the field, it's still possible. Like the Fortran package manager has nothing to do with arrays. But for example, web development, other tools are probably better. But for the array-oriented computing, I think Fortran is amazing. And I want to kind of give one example building on what Milan said. I thought machine learning is a hype, and I wasn't really interested at all until last month when I saw somebody wrote the GPT, the large language model GPT, in 60 lines of NumPy. And I thought, that's not possible. No, they are cheating. And I looked at it, and I ran it locally, and I convinced myself, no, this is not cheating. This is real. It's just 60 lines. So I thought, well, let's write it in Fortran. And I did. And it worked immediately. It's beautifully fast. It's competitive with PyTorch and TensorFlow immediately. In fact, on my laptop, on single core, it beats PyTorch. It's only on my laptop. I'm using very fast, matrix multiplication library from the Apple XLA framework, but it doesn't matter. It's beautiful. And it's beautifully readable. And I think that Fortran is a beautiful language for these kind of language models as well.
I'd just like to go back to this general purpose Fortran question. I love everything that Ondrej said about that. I'd just like to add, yes, Fortran can do theoretically and technically you could write a video game in Fortran, you can write a GUI application, web server, all that stuff. Is it the easiest language to do something like that over, say, Python or some other more general purpose programming languages? Probably not, but I think there's, when we program, there's two kinds of programming. We program to get things done, to do a task. And often we also program out of passion. And when people do that kind of programming and they love a programming language, and many people do love to program Fortran, that's when people make really weird, interesting, and fun stuff and like really creative stuff. And I think that's where you can really see some amazing results in areas that you did not expect Fortran to be useful, like the ones we mentioned. But we hope that, back to the tooling question and the Fortran Lang efforts, our sort of implicit strategy has been to make Fortran programming easy and enjoyable enough so that the broad community writes a lot of stuff and basically builds a really rich ecosystem of Fortran packages. I do believe that there is a very high built-up potential in the Fortran community that has not been fully tapped into yet because of lack of really nice tools, and we're working toward improving that.
Well, if that isn't a call for help and getting involved in Fortran, then I don't know what is. So when I started this episode, or planned this episode, I haven't used Fortran for many years. And quite frankly, through this and through the interview, I was quite surprised to see there's such a strong community of engineers and users of the Fortran language out there. Both modern, but also legacy versions of it. I hope this episode gave you an impression of some of the work and discussions that are happening right now. And as I mentioned earlier, Fortran 2023 should be out this year. And if you are interested in the subject and would like to find out more, I encourage you to follow the links in the episode notes. Finally, I'd like to thank Milan, Ondrej, Tom and Wim for their time. I know how busy you all are, and I really appreciate the time you took to talk to me. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.